interest, that is equilibrium climate sensitivity.
Great. Well, thanks a lot, Saravanan. I appreciate the opportunity to be back in 112 since I was lecturing here 2 hours ago. It's always great to be back here. So I can talk about climate sensitivity, and I think it's useful when you talk about this to start off with some energy balance 101. So how do we describe energy balance? Because fundamentally, climate is an energy balance problem. Energy in, energy out. It's balancing those. So imagine you have a planet. And the planet's in equilibrium. So the top of atmosphere net flux, the planetary energy balance is 0, and the temperature anomaly, the departure from the mean, is 0. So that's some stable climatology. And let's say that you instantaneously quadruple carbon dioxide. Okay, but nothing else changes because you're instantaneously doing this. So the first thing you do is you generate this big top of atmosphere energy imbalance. Energy in is a lot larger than energy out. Okay, so, and we call that, by the way, forcing. So when I talk about radiative forcing, I'm talking about an imposed energy imbalance at the top of atmosphere for the planet. Now, because energy is accumulating in the Earth, the system's going to respond to that. And it's going to respond by warming up. And in fact, if you sort of ask the question, well, I'll get to that in a second. So it's going to warm up, but we also know that as things warm up, they radiate more. So Stefan Boltzmann, sigma t to the fourth. So as it warms up, it drives down the top of atmosphere energy imbalance. The planet is always trying to equilibrate energy. In fact, if you ask the question, why is our climate outside what it is, it's because that's the climate that equilibrates energy for the planet. And if you impose an energy imbalance, you add some carbon dioxide, you do anything else, the temperature will change until the planet's again in energy balance. Now, the way we describe this is through what we call the linearized energy balance equation. And this is the forcing, and then this is the response, which we parameterized as lambda times temperature. So this is the atmosphere, or this is the planet warming up, radiating to space. These two terms oppose each other. Okay, so you have some forcing, then the planet warms up, and it works, and this term erases this. And then this is the net of the two terms. You kind of see what's going on. You have a forcing, and then this decay is this term right here as the planet warms up. Okay, so when you get to equilibrium, the planet is again in balance. So that's what it's trying to do. It's always trying to reestablish energy balance. Now, at this point, you can write the temperature as F over lambda. So in other words, if I apply a forcing of F, the temperature increase I'm going to get is F over lambda. All right. Now, if the forcing is 2 times CO2, then I get what's called equilibrium climate sensitivity. So that is, by definition, the warming at equilibrium you get from doubling carbon dioxide. And that is an extremely important number. And in fact, Scientific American called this the most important number in climate change, because it tells you how warm you're going to get. If the climate sensitivity is close to 0, then who cares about climate change? If the climate sensitivity is huge, then you're screwed. All right, so we need to be able to establish what this number is. All right, so let's do some back-of-the-envelope calculations first. All right, so let's assume for a moment that the Earth acts just like a black body. It's just like it's a billiard ball, or it's something that's very simple. Now, in that case, we can write energy out, basically sigma t to the fourth. And that means that lambda, remember, lambda is the increase per degree. So it's just the derivative of that term with respect to t. Okay, because remember, lambda is how much additional radiation you get per degree of warming. So we can evaluate this. And the radiating temperature of the Earth is about 255 Kelvin. If you plug that in, you get minus 3.8. So this is our first estimate. This is sort of the 0th order estimate of climate sensitivity. If you assume that the Earth kind of just acts like a perfect black body and nothing else changes. And so then we can actually evaluate this. Okay, so forcing for doubled carbon dioxide. That's just a radiative transfer calculation. We kind of know what that is. It's about 4 watts per square meter. All right, not really a lot of debate about that, plus or minus 5 or 10%. And then if we plug in the number we just evaluated, you get a climate sensitivity of about 1. So that's not bad news. I would say 1 would be good news, in fact, if that's right. And so what I'm going to show you next is kind of the evolution of climate sensitivity over time. So this estimate is what we'll call Stefan Boltzmann. Now, Stefan Boltzmann never actually did this calculation, but I'll call it Stefan Boltzmann because we're relying on sigma t to the fourth to come up with lambda. And so they get a value of about 1. I should give credit. This is from Steve Schwartz. This is an update of a nice paper he wrote where he basically has all of the climate sensitivity estimates over time. So, okay, so what's wrong with this? So this is an interesting first guess. It's order of magnitude. It's correct, but it's not right because it ignores a bunch of processes. Turns out that the planet doesn't act like a black body. As it warms up, it doesn't simply radiate to space sigma t to the fourth. A bunch of other things happen that actually make it harder to get rid of energy. And so those things include water vapor increasing. If you increase water vapor is a greenhouse gas, that actually reduces the emission to space. Ice melts. That increases the energy in. So again, that makes it harder to get rid of energy also. And finally, low clouds tend to disappear. Low clouds reflect heat. And there's some argument about that, but I think the consensus is growing that low clouds, you get less low clouds in a warmer climate. And that, again, tends to warm the climate. That allows energy in. So if you take those into account, you'll get a different answer. And the first person to do that was Arrhenius. So 1896, Arrhenius, in a real tour de force, works out his estimate of climate sensitivity. And this is, I should give credit, this is from the Warming Papers by Dave Archer and Ray Pierre Humbert. It's really interesting. I mean, you read it, and it's impressive how much these guys got right, given how little they knew. And so he came up with a number of about 5.5. So here's Arrhenius up here, Stefan Boltzmann. And again, it's an order of magnitude estimate. Given that, it's correct. But there were some things in it that were not exactly right. But still, given what he knew, that was very impressive. So the next big estimate was the Charney report, 1979. This is really the first modern estimate of climate sensitivity. And so this was just about 24 people sitting in a room, and you compare that to the modern IPCC. And it's quite different. It's a bunch of smart guys sitting in a room. They had 2 climate models, the GFDL model and the GISS model, and they had a bunch of physical intuition. They just were sort of saying, how do we think the physics of the atmosphere should work? And what they came up with was probably the most enduring estimate of climate sensitivity. They estimate the most probable global warming for a doubling of CO2 to be near 3 degrees, with a probable area of plus or minus 1.5. So this is, as I'll show you in a second, this is still the modern estimate. So it really hasn't changed since the Charney report. Although I would argue that we know a lot more and we're a lot more confident in it. These people had no idea what the uncertainties were. They were literally just sort of sitting around thinking what was reasonable, and there were a lot of things they didn't know. But nonetheless, they came up with this number that we still use. So then the IPCC report started coming out. So there's a 1990 was the first IPCC report. 1995, second assessment report, 2001, third assessment report, and those all basically, all use the same error bars as the Charney report, and it's just because it's a hard number to estimate, and I'll sort of talk about that in a second. It's a hard problem. Okay, there are a lot of things going on: clouds, water vapor, ice, ocean circulation. It is not. I mean, this is a hard problem. So. You don't necessarily expect, I think given that, this is not that unreasonable. But nonetheless, people started getting criticized, or the scientific community started getting criticized, because they've been working on the problem for 40 years, and they hadn't reduced the error bars. They probably spent $5 billion. So in 2007, they said, this is what I think. I was not in the room, but I'm pretty sure in the back of everybody's mind, they thought, we've got to move one of the error bars. So they moved the bottom one up half a degree. Top stayed the same. Top turns out to be a lot harder to constrain. But they moved the bottom up half a degree, and they came up with a best estimate of 3 degrees. So then they started working, because people are always working on IPCC. So they started working on the 5th assessment report. And this is basically what it looked like. So these are the various ways that you can estimate climate sensitivity. All right, so I'm not going to go over all of these. I'll just sort of briefly go over some. So climate models. You can take a climate model, you can double carbon dioxide, and you can run it out. And you get about 2 to 4.5 if you do that. You can also look at last glacial maximum, 20,000 years ago. You can estimate the forcing. You know the temperature change. If you remember from my equation, lambda is r over r minus f over t. You can just plug numbers in, and you can come up with an estimate. You get 2 to 5 if you adjust it right. You can look at volcanoes. And I should say the thick band is the likely, what they call the likely range. And that means it's 1 sigma. You can think of it as a 1 sigma uncertainty. And so you can get it from volcanic eruptions. You can get it from the last millennium, the last 1,000 years. And so what happened was, and again, I wasn't in the room, but I've heard stories about the discussion. It said, look at this. These are instrumental period estimates. So it's estimating climate sensitivity from the 20th century. And he said, look at all the ink you have down here. You cannot put the lower limit at 2 degrees. You really, I mean, look at all this. You've got to move the lower limit below that. And so that argument actually carried the day. And so the IPCC revises climate sensitivity. It was big news. And so if we go look at our plot, you can see they dropped the error bar back down. And they no longer had a best estimate of what it was. And in fact, they were quite explicit about this. In the IPCC Chapter 12, they actually said the lower limit is less than the limit of 2 degrees in the AR4. This change reflects the evidence from new studies of observed temperature change using extended records in atmosphere and ocean. And, you know, people still talk about this. Just today, on Twitter, Stefan Rahmstorf, who's a well-known scientist at Potsdam, was tweeting about this. And, you know, he basically listed this like, you know, we haven't done anything. But in fact, he had said he had bet somebody that we weren't going to do it. And he won the bet. And then this is Robert Rode said, at this point, ECS may be one of the most studied single numbers in science. There have literally been more than 140 estimates. So people are working on this, and I think we're making progress on this. And so hopefully I'll explain some research we've done that will push our understanding of this problem. So what I want to talk about next is the 20th century estimates. Because if you remember the plot, the reason they pushed the error bar down was because of estimates of climate sensitivity from the 20th century. So what is that? How do you get estimates of ECS from the 20th century? Well, okay, so what you do is you start off with our favorite equation, and then you take estimates of surface temperature from the observations. You can use GISS, HADCRU, Berkeley, NCDC, one of those data sets. And then you have to use forcing from a climate model. There's no way to measure forcing, so we have to get it from a model. And then you make some estimate in the change in net flux and balance, and you usually get that from ocean heat content. If people are interested in the details, you can ask me. I'm not going to go into great detail about how they do this. But you do this, and then you solve for lambda, all right? And then you take this other equation, you estimate ECS. If you know the doubled CO2 forcing, you know lambda, you can get ECS out of this. And again, when you do this with historical records, you get these really low values. And so I've been thinking about this for a long time, and you know, something really didn't sit right. And the basic problem was, why do these not agree? I mean, there should be a single ECS for the climate system. I mean, if you take an Earth, and it's pre-industrial, and you double carbon dioxide, you wait 10,000 years or 100,000 years, and then you average over 1,000 years, you ought to get an answer. You should get one number, okay? Assuming nothing funky happens and, you know, there's some weird, chaotic going to different attractors. You know, there should be one number, okay? So this told me that there's probably some kind of methodological problem with this approach. And so, with my colleagues, Torsten Mjortsen and Bjorn Stevens, during my faculty development leave in 2016, I went to the Max Planck Institute, and we designed basically a perfect model study of the methodology. I mean, we didn't design it. They had the runs done already, but I was the one who came on and said we can use it for this. Essentially, what they've done is they've run their MPI ESM model, which is a fully blown, state-of-the-art coupled chemistry, or not chemistry, coupled climate model. They've run it 100 times, so that's a big computational expense to run a full model 100 times from 1850 to 2005 with identical historical forcing. The only difference is the initial conditions. Okay, so they branch off a different point of the control runs. And in fact, if you want to see what it looks like, this is basically what it looks like. The colored lines are the model runs. The white lines are, the white line is the NASA GISS temp. So then what we're going to do is, for each ensemble member, we know R, because it's a model. We know F, because it's a model. We know T, because it's a model. We know everything perfectly. So we're going to solve for lambda for each ensemble member. And we also know the climate sensitivity, because they've done some forced runs, some long forced runs. So we know everything about the model. We can actually see, does this actually work? Because the idea of this equation is really an assumption. You know, it's an assumption that the TOA flux is going to respond to top of atmosphere, or the top of atmosphere flux will respond linearly in surface temperature. So we can actually test this. And when we do this, this is what it looks like. So this is a PDF of lambda from the 100 runs. You can see we don't get a single value. The dashed line is the model's true value, which we get from a 4 times CO2 run. And you can see that the different ensemble members can get values that are far from the model's true value. Okay? And this is important, because remember, we only have one realization of reality, which is the observational record. We don't have an ensemble of Earths. So that means that if you try to evaluate climate sensitivity, try to get lambda out of the historical record, you might get the right answer. You know, if you're lucky, you'll get an answer close to the middle. But if you're not lucky, you're going to get an answer that's way out on the wings, and you're going to get the wrong answer. Okay, you're not going to get something that's very close. And again, this is entirely due to internal variability. It's not due to any, it's just due to the fact that the climate evolves differently, and that this assumption that the TOA response is proportional to surface temperature may not necessarily be a good one. Now, we can convert this, as I said before, we can convert this to ECS. And so what does a PDF look like in climate sensitivity space? This is what it looks like. So you could get one ensemble member gives you about 3.8, 3.87. One ensemble member gives you 2.08. So you could get almost 2 to 4 degrees in your inferred climate sensitivity. And again, we know what the real climate sensitivity of the model is. It's 2.9 Kelvin. So basically, if you try to take 20th century estimates and say the climate sensitivity is low, you are on very weak ground, because you just the method doesn't work. It doesn't actually give you the correct climate sensitivity. If you're lucky, it does, but how do you know if you're lucky? You're just getting a number. Yeah?
Are you going to tell us why the different analyses gave different results?
You mean the different ensemble members give you different results? Or?
In the curve you had originally of the estimates from the 20th century, some were real low, but they weren't all.
Yeah, I'm not.
They're all using the same data.
That's right. They're all using the same data and the same method. I'm not going to talk about that. That's a real detailed discussion of methodology. You know, they all, basically, you've got to solve for lambda, and they all have different ways of doing that. So some of them do essentially almost a data analysis thing where they have a model that they kind of constrain with observations. Others, they pick periods at the beginning and end and subtract them. Others do regression techniques. So they all have different methodologies of how you solve for lambda, because there are lots of different ways to do it. But that's actually, and there are a few people in there that are trying to get low answers because that's what they do. And, you know, so they're tweaking every single parameter to get a low answer. Yeah?
So the 2.9 value, is that for a model run of 1,000 years?
Yeah, so they have they've run the model for many, many thousands of years. So they actually have a model, they double carbon dioxide, and they just let it run. And so they have thousands and thousands of year runs of the model.
What you are saying basically that this is just too short, that it doesn't really settle on the climate structure?
Yeah, okay, so...
Depending on the initial condition?
Yes, that's right.
Really the climate what you are seeing?
Well, I'll explain what it is next. So let me explain why this happens, okay? All right, so what we're going to do is, here's the ECS. So what I'm going to do is I'm going to take the 5 hottest members and the 5 coldest members, the members with the 5 highest ECS and the members of the 5, and I'm going to average them and I'm going to subtract them. So I'm going to show you a bunch of things that are all going to be the difference of the high ECS minus the low ECS models, okay? So the first thing to do is let's look at the warming pattern. And so this is the normalized warming. So it's the warming at each latitude divided by the global average warming. And what you see is that the high ECS models have a lot of warming in the southern hemisphere. This is right where the sea ice is. They have less warming in the tropics and more warming in mid-latitudes than the low ECS models, okay? So this is and I'll explain why why you then infer a higher ECS if you have this pattern of warming. But this is important. A lot of warming here and less warming here. So remember that. All right, so what we're going to do is we're going to start off again with our favorite equation. And remember, we can solve for lambda by doing r minus f over ts, just algebra. So what I'm going to do next is we're going to break this down by latitude. So I'm going to come up with a lambda at each latitude, which is just the r minus f, the TOA flux, minus the forcing at that latitude, divided by ts. And if you just integrate this, you get this. If you just integrate this, you get that. Okay, so this is what the lambda looks like at each latitude. And again, this is the difference between the high lambda minus the high ECS minus the low ECS. So what you see is you have a big spike of energy in for the high ECS models in the sea ice region. So you can probably guess what's happening. You're losing sea ice. Losing sea ice, you get rid of reflective surface, you have more energy in. And then you have more energy in the tropics also. So in both of these regions, the high ECS models have more energy coming into the Earth system. Now, so let's look first at this region right here, and just tell you that's 25% of the effect. 25% comes from the sea ice region, and then 75% comes from here. All right, so I'm going to show you next is sea ice. So for each ensemble member, we've calculated the change in sea ice over the run. So the last decade minus the first decade, and then I'm going to subtract the high ECS models from the low ECS models. And what you see is that the high ECS models, their negative values here, they lose more sea ice than the low ECS models. And this is not climate change. This is internal variability, because not all of the ensemble members do this. So what it says is if you happen to have an ensemble member that loses a lot of sea ice, you're going to infer from that a big climate sensitivity. And the reason is because along with that, you have a lot of energy in. Your R minus F is big. Now, it's not because it's a response to climate change, because it's not, but it correlates with it. It happens to be happening at the same time, so you're going to alias the loss of sea ice, which is due to natural variability. You're going to alias it into the warming. And if you do that, you end up with a big ECS, because you're losing a lot of ice. So you'd infer from that a huge ice albedo feedback. But it's not real. It's a variability. It's not due to warming. It's not due to global warming. You know, in the interest of time, I'm not going to talk about this other than this is just a temperature effect. The fact that the tropics warms less means you radiate less energy to space. You're losing less energy, and that also tends to infer a larger climate sensitivity. So we kind of understand what it is. It's the pattern of warming among these. And so if you're unlucky, then you're going to get an answer that's actually far from reality. And I should say, give credit where credit's due. A lot of people have been working on this understanding the pattern. I should point out Chen Zhou, former graduate student here, graduated in 2014, wrote one of the best papers about this, looking at the impact of cloud variations on the Earth's energy budget, and again making the argument that we've been in a pattern, and that's these two papers also, Kate Marvel and Tim Andrews, also showed that we've actually been in a pattern that's driving us towards low climate sensitivity. So the reason these estimates of historical warming are low is bad luck, that we happen to have a pattern of warming that's implying a low climate sensitivity, but it's not real. The climate sensitivity is not actually as low as the pattern of warming. So I got to the end of this, and I thought, well, that's discouraging. And I also decided that we've taken these 20th century estimates as far as we can go. I don't see any way to correct these to get the right answer. So then I started saying, well, what other ways can we use to estimate climate sensitivity? I started to say, let's think about internal variability. So internal variability, if you look at like the last decade or two, it has a bunch of advantages. First of all, we have really good observations for the last 20 years. Secondly, the changes are not forced. And that means you don't have to worry about forcing. If you go back to the ECS calculations, the biggest uncertainty is really forcing. And it's also this pattern effect. But the forcing is this huge uncertainty, because we really don't know, how aerosols affect clouds. So this indirect aerosol effect is really a big uncertainty. And there's really, I don't see any way without a breakthrough in quantifying that. I don't see a way to get around that, or the pattern effect. So let's look at short periods, recent short periods that are dominated by El Nino cycles, where that's the temperature change. And then you can ignore forcing. So forcing goes away. So, and I should say this work has all come out in the last week or two with my co-author, Piers Forster. And so let's think about this. How could we measure ECS by using interannual variability? So, okay, let's start off with our equation. This basically tells us that if forcing, we probably know. If we can make an estimate of lambda, we're done. Okay, so the goal is to estimate lambda. So one way we could do this is we can use observations. So we have series data of TOA flux. So series measures this. Forcing is not important, but still we're going to use an estimate of forcing. But it turns out to not be very important for this problem. And then we have surface temperature. We have lots of good surface temperature records. So we can basically solve for this. And we can estimate what lambda is. And let me just emphasize that the temperature changes that we are looking at. So we're looking at the response of this to temperature changes. This is what the temperature record looks like over the series period. And you can see it's not global warming. It's dominated by internal variability, things like El Nino cycles. Big La Nina here. This is a big El Nino. I mean, these changes, there's probably a trend in there, but it's hard to pick it out because the year-to-year variability is so large. All right, so let's go back to here. So how are we going to do this? Well, I just moved forcing over to this side of the equation, and I'm going to plot R minus F on this axis. Yeah, I may give up on this. You can still see. R minus F on this axis versus temperature on this axis. And ta-da, that looks terrible. All right, so first thing you realize is this is not very good, not a very good correlation. In fact, the error bar is bigger than the number. So, I mean, you can't even rule out a slope of 0. So, but you know that can't be right. It can't be a 0 slope. But nonetheless, this is not good. And there's actually a bigger problem than this, which is this, as I told you before, is the response to interannual variability. But what we want here is not the response to interannual variability. It's the response to double carbon dioxide. And people don't really know, or nobody's really looked into how these relate to each other. And this disconnect between what we can measure, which is this response to internal variability, and what we want, which is a response to long-term warming, is one of the reasons why people have not spent a long time looking at internal variability to estimate ECS. So I'm going to boldly try to make that adjustment. We're going to look at this. We're going to try to figure out how do we map interannual variability to long-term warming. And essentially, this is what we're going to do. So we're going to take what we observe, which is this value right here. So this is the slope of the regression. And we're going to multiply it by a transfer function that we estimate from climate models. So it's lambda 2 times CO2. So that we get this from a forced climate model run, and we get this from a control run that doesn't have any forced change in it. And so we get a ratio, and then we just multiply it by this, and this gives us what we want, which is the response to long-term warming, okay? And, you might think it's a little squirrely. We'll talk about that at the end. And so if you do that, then this is what ECS becomes, okay? So it's F, forcing, divided by the observed lambda, times this transfer function. Now, it turns out that the CMIP5 doesn't have doubled CO2 runs that we could use, but it does have 4 times CO2 runs we're going to use. So we're just going to substitute those. We're going to assume the lambda response to 4 times CO2 is the same as lambda is to 2 times CO2. That may not be right. You can ask me about the uncertainties involved with that. But that's what we're going to go with. Okay, so now we can calculate ECS. We have arrived. So first thing we can do is we can put in a probability distribution for forcing. So we get this from the PDR MIP, Precipitation Driver Model Under Comparison Program. And so this is basically just a normal distribution centered at 3.7 watts per square meter. And we're going to plug that in here. We have observations. This is from the series data. We use a Monte Carlo method to come up with a distribution of slopes. We can plug that in there. And then this we get from the models. So here's what the distribution looks like from the models. It's an iffy switch. So what we're going to do then is we're going to Monte Carlo this. We're going to take 500,000 samples from each distribution. We're going to plug them in, and we're going to come up with an ECS for each one, and then we're going to plot up the distribution of ECS. Okay, and what you end up with is this. Ta-da! And this looks kind of like what you expect. You get a big peak around 3, maybe between 2 and 3. You have a long tail to high values, and then it goes to 0 towards 0. The likely range is 2 to 5.7 Kelvin, with a median of about 3.3 Kelvin. All right, so this does not support the very low values that the historical record gets. So it's another estimate that says the ECS is higher than the very low instrumental estimates from the 20th century. Now this is okay, but it's a bit on the disappointing side in the sense that it doesn't, it's not a great constraint on the upper end. These values out here, which I think are physically unreasonable, the climate sensitivity is not 7 degrees. We kind of know that. And yet we're still getting a reasonable probability. And then I won't talk about that, but there certainly could be decadal variability in what we measure from series. So in the paper I showed before, the ACP paper with Torsten and Bjorn, we also came up with a revised energy budget framework. So remember, the energy budget, the canonical linearized energy balance equation parameterizes everything in terms of surface temperature. Okay, so the TOA flux is a response to surface temperature, but why pick that? Why not pick something else? So we tried a different way to describe the energy balance. And we used atmospheric temperatures instead of surface temperatures. Then we did that, we replaced lambda with theta. And so theta is now converts the change in atmospheric temperature to lambda. And I should just say this is tropical temperatures, and I won't go into why that works. You can ask me if you're interested. Here's the time. Now, the advantage of this, you might say, who cares? Why are you doing this? The advantage is that it explains the scatter and the series data a lot better. I'll skip this over. So here are the two distributions we get. So here's the distribution of slopes. Remember, we get lambda from the slope of temperature versus R minus F. And really, it's not well constrained. That's because it's a crappy fit. Remember the cloud of points? But this one is a much better fit. And so we actually can constrain this slope a lot better because atmospheric temperatures correlate with TOA flux better. In other words, atmospheric temperatures are a better controller of planetary energy budget than surface temperatures are. So now that we have this revised framework, we can calculate a second version of ECS. Now in this framework, if at equilibrium, you're solving for the atmospheric temperature. So this part right here is the equilibrium atmospheric temperature change, right here. So in order to get ECS, which is the surface temperature change, you have to multiply by this term, which is the equilibrium surface temperature increase divided by tropical atmospheric temperature increase. So it's very similar. It just has this one extra term on it. And otherwise, the equation is the same. Here's forcing. This is what we measure. And this is a transfer function that we're getting from climate models. And so again, we can do the same thing now. We can go through and we can Monte Carlo this.
I'm sorry.
Yep.
Quick question. The function that you get, that transfer function,
Yep.
you use the radiant transfer equation to figure that out? Or?
No, I used, basically I used the climate model output. So the climate model has a radiative transfer function in it.
Oh,
Yeah.
okay.
All right, so basically I have the same, I have distributions for all of these terms. This is the forcing terms. It's the same one. This is, again, is from observations. Notice how narrow it is. Spoiler alert, this is going to give us a narrower climate sensitivity estimate. This is what I get from the climate models. I have to say it's weird. It's bright. And then whenever I point at my hand, I can see it. That function in the middle is the I get from climate models, and then the T over TA I also get from 4 times CO2 runs. And if you want to know the details, ask me about them. I can tell you about the uncertainties and all that stuff. But just in the interest of time, I'll just tell you that's where I get them. And so you plug all of them together. You randomly pull numbers from each distribution, put them together. This is what you get. And this actually is a much better constraint. Okay, so this is 2.4 to 4.5 Kelvin. Remember, the other one went well north of 5. And, we don't have sort of that long tail. We do have some values, but the low value is 2.4 Kelvin down here. The high value is 4.5. The median is 3.3. So what we concluded from this is that the upper end of the IPCC ECS range is about right, 4.5 degrees. But the lower end of 1.5 is way too low. And we would say it's 2.4. Obviously, you have to look at all the data to come up with something. But I would be willing to bet that the next IPCC report is going to have a much higher lower estimate. So the lower estimate will be north of 2 degrees. That is my bet, because we understand why the low values are low, and most of the other values are giving us higher numbers. Okay, so it's useful to look at this equation because, a lot of this stuff comes from models. And there are people, I just found a random picture on the internet of people who don't believe climate models. And so it's useful, I don't know who these people are, but it's useful to go through and to ask yourself, do you believe these things? Okay, so we can go through the terms and ask if we believe them. So the forcing. I believe the forcing. Okay, if you think we can't calculate doubled CO2 forcing, then we can't calculate anything. Okay, it's a radiative transfer problem. Maybe there's a little uncertainty with the distribution of clouds, but I mean that is not the hard part of the problem. Okay. All right. So the theta, see that term right there. We have observations. I think the observations are pretty good. So I think those are unlikely to be wrong. This term right here comes from models, but the models have demonstrated a good capability of simulating the pattern of warming. It's one of the things they've done a really good job of. In addition, we understand the physics of the atmosphere-surface connection. It's moist adiabat. And so we can compare to data, we can compare the models to data, they look pretty good. Okay, so I think that term is believable. So the term that you really have to wonder about is this term right here. Do we understand this transfer function? And this is the thing, we don't really have anything to compare it to. It has a lot of physics in there that maybe the models aren't getting right. So we need to really think carefully about this. And so the first thing to realize is, while we can't compare the ratio, that ratio to observations, we can compare the numerator. So the numerator is from the control run. It's the response of the models to interannual variability. And we have measurements of the response of the climate system to interannual variability. And I won't show you, in the interest of time, I won't show you plots. I have a plot. You can ask me if you want to see it. And so they do pretty well. About half the models do a really good job simulating the observations. The other half don't do quite as good a job. But nonetheless, the models look reasonable. If the models were really missing some big feedback, some big important process, it would be hard to imagine they would do a good job. So what that means then is you need, in order for this to be wrong, if you assume the models are getting the numerator right, then there has to be an error in the denominator that's not reflected in the numerator. And obviously you can imagine that, but we can also do some tests. So we can take a model. In fact, my colleagues at Max Planck have actually run their MPI ESM 1.2, and they ran it with different cloud feedbacks. And so let me show you the results of that. So there are three versions of the model. All right, so there's what they call the standard model. That's the model that running for CMIP6. That has an ECS of about 3. So if you double carbon dioxide, you get about 3 Kelvin of warming. Then they have an iris version of the model. That has a negative cloud feedback. They've done is they've tweaked it so that the clouds produce less anvil, so you get more infrared out. That has an ECS of about 2.6. And then they have a version where they tweak the entrainment to give it a really big cloud feedback of 5.2. So they have the same model with 3 different versions of the cloud feedback. And then we can do is, with those models, we can calculate theta IV and theta 4 times CO2. And sure enough, you see that when you change these feedbacks, these values change. You know, the model that has the big positive cloud feedback has a value closer to 0, which is consistent with a high ECS. The value of the iris has a much lower value. It's a factor of 2 difference, consistent with the factor of 2 change in ECS. And similarly, you see a similar change in these. So it says that if you change the feedbacks, you change these two about equally. If you look at the ratio is relatively consistent at the 15% level. So it says that if there's an error, if your model's missing a feedback, and there's an error in the numerator, there's going to be an error in the denominator, and they're going to about cancel. Now, this is a single model result because it takes a lot of runs. I don't expect there to be a lot of models you can test this in. So it's some evidence that this is a believable process. Again, I mean, you have to take it with a grain of salt. And I think that, if I were a student looking for a high-impact problem, if you could come up with a good theoretical argument for why this ratio should be close to 1. If you look at the model ensemble, it's about 1. If you could come up with a good theoretical argument for why it should be 1, that would be a really important result. So that's basically it. So I'll just wrap up the conclusion. I talked about a lot of things. Hopefully people were able to follow it. So the first thing we did is we critiqued the estimates of ECS from the 20th century. And those are order of magnitude. They're good at the order of magnitude, or factor of 2. They're not good at the 10% or 20% level. So the fact that you're getting low values should not be used to actually say the climate sensitivity is 2. You can't tell 1.5 from 3. You can tell 1.5 from 10, but not from 3. So you really can't argue that the climate sensitivity should be on the low end from those. And then we used interannual variability to estimate that ECS is likely in the range of 2.4 to 4.5 Kelvin. That should actually be 4.6. In the final paper, it's 4.6. And this is, I think, all of these estimates. Here's the way I sort of think about this problem. There are a lot of estimates that come up with sort of these reasonably big ranges, but a lot of them are independent. And so you sort of look at a lot of kind of big independent measurements with large error bars. You can actually constrain it a lot more tightly than that. And so I think we're coming up with a lot of these independent measurements, and I think that in a few years when the IPCC 6th assessment comes out, you're going to see a much reduced climate sensitivity. And lastly, I'll say, this is a good problem for anyone who thinks about it, that's really the key parameter. If we could identify that, we could constrain ECS to about an uncertainty of about 1 degree, because most of the uncertainty in that spread is coming from that parameter. So anyway, so I'll wrap up there and happy to answer questions. Thanks. I would say, my opinion is that I would not pursue the traditional lambda method. I think the theta method works better for the reason I showed that the observations are more tightly constrained. Yeah, that's right. I mean, it's a better constrained observationally. And so it turns out that makes a big difference at eliminating. I mean, the thing you got to remember is the ECS goes as 1 over lambda. And if you look at the observations, there's a non-zero chance you're going to get a lambda of 0, and that's what pushes that tail out to infinity, basically. And so that's why it's really hard to constrain the upper end of the limit with that method. Now, the theta method, because it's better constrained, you never get theta. In fact, this actually shows the various estimates. These black ones are the distributions from the lambda method. The red lines are distributions from the theta method. These values close to 0 push the tail out to infinity. I don't know any way to get rid of those. Whereas the theta method, if you regress against atmospheric temperature, you get a much better constraint of what theta is. Yeah, you want to have very little uncertainty here, and you don't want values close to 0 because that's going to confound your PDF. If you get close to 0, your tail goes out to infinity because it goes as 1 over this. Gunnar? So I used ECMWF. I think the problem is not with the quality of the atmospheric temperatures. That is not what's driving the spread. What's driving the spread is that this is my theory, at least. I've actually sort of thinking about this now. What's driving it is that there are two things that regulate TOA flux. One is radiation from the tropics, and that's essentially determined by tropical upper tropospheric temperatures. The other one is high latitude albedo, and that's not controlled by tropical atmospheric temperatures. And so what you're seeing here is the spread that's from the high latitudes. And so I think there's probably a way to write a slightly better energy balance equation that has 2 temperature variables, one atmospheric temperature and then one variable that explains the high latitude surface albedo. We'll see.
Any other questions from the back?
Yeah, well, not a new energy balance equation, a new linearized energy balance equation, not rate of transfer. You're right. So I mean, the whole idea of the energy balance equation is you're trying to find some variable that explains top of atmosphere flux. What's the control on TOA flux? And so in the old days, it's all global average surface temperature. That's one way to do it. And that doesn't work. That works okay. That's sort of the order of magnitude estimate, but it's not great. But so you can think about other ways of doing it. Use atmospheric temperature. We tried that. That does better, but I think there's a way to do even better. Maybe use two variables. Maybe use a temperature squared term. Use temperature gradient. There's all sorts of ways to do it. And I think that is a good active area of research.
Really? Interesting.
Yeah, Yang?
Yeah, I just want to follow up your last point about the ratio of the two CF, the force one versus internal variability. So in addition to explaining that the physical mechanism, I was thinking about applying some observational constraints to that.
I'm not sure I understood. Say it again. To which you're talking about the ratio, theta, IV?
Yeah.
I'm not sure what observational constraints. I mean, this is why it's a good problem. Maybe I haven't thought of any observational constraints to that ratio, but if you could think of any.
They are all model output. Eventually, you will get a good answer by giving a physical argument.
Right.
It's all model constructed based on physical mechanism. So you will get that. But I think more important is looking at real world, how to narrow that position.
Yeah, no, I think if you have any ideas, that's certainly, as I said before, that's a high impact result if you come with a good theory.
So I have a related question. So you're looking at the global mean. If you look at intraannual variability, the surface temperature pattern is dominated by El Nino, with narrow tropical warming, a lot weaker elsewhere.
Right.
But the global warming pattern is weak in the tropics, very high. So it's very, you can average them globally and get a number, but they're very, very different beasts, aren't they?
Yeah, no, I mean, you're right. That's why I think, it's as Yang implied, and you do, it's that's where, if this is wrong, that's where it's going to be wrong, I think. And I think that's, you'd like to come up with a better theory. You'd like to come up with a theoretical argument for that.
Yeah, so it kind of seems like a lot of the models have been based on either like the global average surface temperatures, like in general, and then there's been also been like the atmospheric side. Do you know if there's been kind of attempts to use like ocean temperature, like at various steps, to kind of like balance out and kind of like coupling all the different methods?
Well, certainly the models, the coupled atmosphere-ocean models have temperatures everywhere, but you wouldn't want to use ocean temperatures in sort of in this kind of equation, because ocean temperatures below the surface aren't going to have a direct effect on TOA, on top of atmosphere radiation. They would affect it through something else, but through maybe changing the surface temperature. But photons from 100 meters in the ocean don't get out to space, so they're not what's really fundamentally regulating the energy balance. Yeah.
How are these calculations being changed since geoengineering is starting to play a part to help, I guess, when they do cloud seeding to help with rain? What effect do you see it altering the future of the climate models that have already been output?
Yeah, I mean, I think I don't think there's any sort of global effect of cloud seeding. At least I've never seen anybody do that. I mean, ultimately, if they do start geoengineering, that would go in as a forcing. That would be part of the forcing term. So, that's where that would enter into the problem if we get to that stage. Courtney?